And so our first presentation is Bob. For how many people here know Bob? Okay, not a plurality, but Bob has been working in Montana for, well, I think probably more decades than he might want me to say. He went to school with Susan Luke. He was one of the Indiana field school people who went to field school here and didn't leave. He's emeritus professor at Allegheny College, which is in Northwest Pennsylvania. And he is a source of all knowledge sedimentological in the Cretaceous and Tertiary in Montana. And I don't know what I'm forgetting to say, but I'm just going to hand it over to you, Bob, then. I'm going to hit record. Oh, I'm not going to hit record.
Yeah.
We want.
Just no lights.
Off?
What's best?
That's good.
That's
good.
great. Okay.
Thanks, Larry.
All right. Let's see if I can get back up on this.
Okay, are we good to go?
We're good to go.
And you can hear me okay?
Yep.
Yeah.
Everybody's nodding.
Yeah, okay. I'll hear the snoring in a couple minutes. Yeah, but much of the material in this presentation comes from recent work by myself and Teresa Schwartz and Colleen. And what it fundamentally involves is a study of the Renova Formation. And in that we include lowland creek volcanics. And it involves a study of that unit of rocks to tell us something about the tectonics, landscape, and basin evolution in this part of Montana. And ultimately, as you will see, not only just during the Paleogene, but we can step back into the time period associated with unconformity development on top of basement rocks, which are everything from Mesoproterozoic to Mesozoic rocks, the ones which have been contractionally deformed. So there's two stages of history that we can address, one directly, and then stepping back by inference into the unconformity period. So to start out, to show the study area here in red, it lies within the Basin and Range physiographic province. And I think I should just identify some of the features, some of the intermontane basins and the mountain ranges for those that might not be not well informed, aware of it. Okay, I'll get there. On the western side of the study area is the Flint Creek Range, the Anaconda Range, and I'm just going to stick to the main ranges involved in the talk today. On the other side of the study area, the Boulder Mountains, the Highland Mountains, and the East Pioneer Mountains. And the basins that I'm going to be discussing are the Deer Lodge Basin, a little bit about the Northern Big Hole Basin, Deer Lodge Basin, and the Melrose Basin. Let me see what else on this slide. Yeah, the Missouri and Columbia River System. The study area includes headwaters of the Columbia River System, up like that to the northwest, and then headwaters of the Missouri System, which drain from the Big Hole down a basin here. I call it the Deep Creek Basin, through the Big Hole Gorge, and let me see, over into the juncture between the Divide Basin, Melrose Basin, down and out like that. So there's two primary drainage systems, the Columbia River System, this is going to come into play in the findings, and the headwaters of the Missouri River System. Basin and range, largely accepted that it is extensional fault related, extension starting with Eocene tectonics, about 53 MA, in the Deer Lodge Basin, but significantly deformed beginning in the early Miocene.
Can I just, sorry, can I just interrupt? Can you guys see his cursor? Okay, because
Oh,
you
did
lost
that?
you lost,
It disappeared on me. Where did
yeah.
that laser thing
But
go?
everybody, people are nodding. They can see your cursor, so it's okay.
Well, for some reason it evaporated after we set it up. Okay, Renova Formation, a little bit of background on that. Here's a stratigraphic column showing the Renova Formation between two major unconformities. This would be the sub-Cenozoic unconformity, where in the Deer Lodge Basin, lowland creek volcanics lie upon everything from Mesoproterozoic to Paleozoic and Mesozoic strata, as well as eroded granitic plutons, late Cretaceous. And we have the Renova Formation itself that consists primarily of siliciclastic rocks ranging from volcanic rich or volcanics themselves right at the base to mudstones, sandstones, conglomerates up here, mostly fine-grained, and then capped by this unconformity here. Probably the main point in leaving this slide is that it is a stratigraphic package that represents the first time of deposition following contractional tectonics during the Mesozoic and a little bit into the Paleocene. Okay, so let's go down. Structural setting. So here's a study area in red. The basin and range runs with regard to just a study area here. So the study area is within the basin and range, but making up the infrastructure underneath that is the severe fold and thrust belt contractional structures. And the study area also lies within this gray shaded area, which is referred to as a Cordilleran Anatectic belt. And that's a long, narrow zone runs north-south that contains abundant late Cretaceous to Eocene granitic plutons, many of them being two microgranites, as well as partially melded granitic rocks or eutectic rocks or anatectic rocks. Okay, so in addition to that, the Cordilleran Anatectic belt contains, indicated in black, metamorphic core complexes. This is the Anaconda Flint Creek Range complex. In the literature, it's referred to as the Anaconda core complex, metamorphic core complex. And we have findings that we interpret that it doesn't meet all the criteria of a core complex, and we tend to not consider it a core complex, and that's why I've sort of outlined it in heavy gray just to designate its presence, just to point that out. Let me see, anything else? No, let's go down to the next slide. Okay, so the topic really has to do with basin evolution and tectonism during the time period during the Paleocene through the Eocene, the Oligocene into the early Miocene. How do you get there? Well, the questions that we posed or the topics that have to be addressed are primarily what was the landscape, both during Renova time and before Renova time, so pre and syn depositionally. Compositional data. The composition of the basin fill and the source areas provide input for those topics. The history of magmatism has to be addressed, as does a history of pluton exposure in the various ranges. And one of these things we'll see is that by the time of earliest deposition, granitic plutons were exposed in all mountain belts surrounding the intermontane basin. So how do we get to this? How do we address these questions? Well, the key data is considering the structural setting, in this case, contractional structures associated with Cordilleran tectonics, followed by extensional tectonics and normal faulting. That consideration plus identifying depositional facies, paleocurrent data associated with the different systems, class composition, and detrital zircon. And I'm getting real dry mouth here. Let me take a sip. There we go. Geologic map of the study area. We looked at 51 different sites in detail, as well as a number of other sites in a cursory manner. Basins are in this pale brown area. This would be the Deer Lodge, Deep Creek, Divide, the Melrose Basin down here. Here's Mount McCartney. And a couple things to pull out of this map in particular is not just the number of data sites, but the presence of the Anaconda Flint Creek Detachment Fault running up through here. We refer to this as the Anaconda Detachment Zone. That's an old label. And the other thing is, notice on the geologic map, this is the present, all the plutons, all the granitic plutons flanking the intermontane basins. It's the West Pioneers, East Pioneers, and so on. Okay, how do you define the paleogeography? I already indicated that facies are the key indicator for paleogeography. And in looking at the Renova, the following facies are identifiable: alluvial fan facies, debris flows, tributary fluvial systems coming out of the mountain ranges, the ancestral mountain ranges. These are collectively referred to as the basin margin facies group. When you look at these, plus measure paleocurrents, it directly points to the upland source area. So there's no question as to the source for the alluvial deposits flanking both sides of the basins. And then their basin interior facies, let's start down here. There's some thin lacustrine deposits, thin to relatively thick, alluvial plain deposits, including paleosols. Of primary interest to us were fluvial deposits, which run from fine grain to coarse grain sandstone to conglomerates. When you consider their paleocurrent structures, they tell us a couple things that are of key importance. Number one is, given that the paleocurrent directions are parallel to the axes of the basins, we know that they are trunk drainage systems within the basins. We refer to them as axial-fluvial systems. And integrating all the different axial fluvial systems, we can figure out, or did figure out, the regional drainage system for the entire study area. So this is primary input data that leads us to this type of information. Let's just look at some examples. First of all, starting out with coarse basin margin facies. These are all from the Deer Lodge Basin. This is along Racetrack Creek. It's a carbonate class debris flow. This is a zoom in on the size of some of the boulders. It's a 15-centimeter scale. But this tells you that you were proximal to a carbonate uplift, nearby deposition. It came just from immediately to the west in the Flint Creek Range. This is a little south there. This is near the town of Anaconda, just north of it a little bit, but it's a granite boulder bearing debris flow. And this is a granite boulder here. This is where one was, and there's another one over here. And these are all large lowland creek volcanic class, actual volcanic rocks. And these were coming down the slope away from the Flint Creek Range. Here's a tributary fluvial deposit. Paleocurrents tell us that it was also coming out of the Flint Creek Range and with various constituents within that. We jump over to the Divide Basin. This is a debris flow deposit coming out of the Highland Range and quartzite clast, granite clast, mudstones, limestones, and so on. But it's these clasts that you can use to define the composition of the source rocks in the adjacent ranges. And then down into the Melrose Basin, this is near the town of Glen on the west side of the river, but these are all debris flows channelized and then massive flows containing large blocks of volcanic rocks, some Paleozoic, clast, and so on. So let's see. Oh, this is McCartney Mountain in the Melrose Basin. This is on the southeastern side of the McCartney Mountain, but a nice debris flow showing McCartney pluton, source rocks, a granite boulder, limestone, coarse lithic sandstone, probably Kootenai. And then along the southern perimeter of McCartney, there's one exposure that shows axial fluvial deposits, which I haven't gotten to yet, but this is imbricated clast in a coarse-grained axial fluvial conglomerate. But coming down off of McCartney is this debris flow, all of Cretaceous siliciclastic debris. So it's a nice alluvial capping of this fluvial system. And then there's the axial fluvial bodies. I'm not going to go through all the physical characteristics of them, mainly because I just want to get through this and use them as tools. But this is in the northernmost part of the Deer Lodge Basin. Coarse grained sandstone with an abundance of cobbles. This is two mica cobble. The source rock would be the Mount Powell batholith and the Flint Creek Range. There are also clasts in this Valcorn Mountain volcanics being derived from the east side of the basin in the Boulder Mountains. This image here shows the conglomerate just along the northern side of the town of Anaconda, close up at the size of the cobbles and the boulders, mostly Mesoproterozoic clast, but a real abundance of Mesoproterozoic limestone clast as well. The paleocurrents, as I've already mentioned, for these bodies are parallel to the basin axes. This fluvial body, it's northward toward the Flint Creek Basin. Here it's southward towards the Deep Creek Basin. So bipolar. Come over to the Divide Basin, Cabbage Patch Formation, just more of the same, a coarse-grained, quartzo-feldspathic, lithic-rich fluvial body. Down in the Melrose Basin, this is along the western side of McCartney Mountain, beautiful conglomerate. And these boulders, some of them are loose, but all of them are coming right from the base of the conglomerate. This is a close-up of a granite boulder in place, but this is actually being derived from the toe of an alluvial fan coming off of McCartney Mountain, where the boulders are being reworked by the fluvial system and being deposited. Paleocurrents here are aiming right down the Melrose Basin around the southern tip of McCartney towards the gap. So here's a basin fill model that we put together for another purpose in the past, but it shows, in essence, the architecture of the fill in these basins. On the surface, alluvial fans, various basin margin deposits, different types, including mud flows, debris flows, and so on. Axial fluvial systems, moving parallel to the axis. Here we have two intermontane basins with flow through a a gap in the mountains joining, and on out in the subsurface, you would have this, not to say this is the architecture of the basin fill, but it's a type of thing which there's evidence that this depicts basically what is happening. Coarse grain, especially coarse grain fluvial deposits near the base, axial fluvial out of the plain, lacustrine deposits, and then cross sections of basin margin deposits on the perimeter. Integrating all the paleocurrent data together, the diagram on the left is related to this inset right here. This is a paleo drainage map and a paleogeographic map for southwestern Montana. This is based upon previous studies. This here is a summarization of the large map on the left, and this shows our paleocurrent data both for basin margin deposits. Here's the white are all basin margin, and blue are axial fluvial bodies. And what you can see is that I've broken this down into the northern and the southern Deer Lodge Basin. This is the northern basin, southern basin, but the paleo flow for the fluvial systems through the northern basin were northward towards the Flint Creek Basin as it is today. Now, a difference between this and today is that in the southern part of the Deer Lodge Basin, our evidence, remember that coarse-grained conglomerate at Anaconda, lots of data there, but the axial flow was towards the southward region. And I'm choosing to say that it went through here into the Deep Creek Basin and down like this. And you say, well, why not over here? There's a number of arguments why it didn't go through here, including paleo flow over here in the Divide Basin. It's to the south. That would lead one to think, oh, well, maybe it went through here. But the composition of detritus in this part of the basin and the Northern Divide Basin does not match at all. There was not detrital exchange between this basin and this. So we had two different systems. This system here, okay, I'm interpreting that it went from the Southern Deer Lodge into the Deep Creek, joined with drainage out of the Northern Big Hole Basin up here through the Big Hole Canyon, met the drainage from coming down from the Divide Basin down through the Melrose Basin and on out as such. So the scenario is one of axial drainage. I'm referring to this as the headwaters of the ancestral Missouri River system, headwaters of the ancestral Columbia River system, and in all cases, the basins are flanked by basin margin deposits indicating transport, conversion transport into the basin. Now, there's more sites that we analyzed than these where we don't have paleocurrent data, but the composition of the basin margin deposits match adjacent uphill source rocks. So even though we don't have paleocurrent indicators, we know, for example, basin margin deposits up here came from the Flint Creek Range, if that made any sense. I sort of jumped around on that one. Another drink of water. Okay, conclusions thus far. During Renova time, now we know that there were elongate mountain ranges with intermontane basins in between them. I didn't make a major point out of this. This will require talking more about compositional analysis. I told you a little bit to try to get you there, but the ancestral mountains contained rock types similar to those of today. And we also know that there were granitic plutons exposed in all of the ranges, as there is today. So there's real parallelism here, which is telling you something about, instead of just basin or range, fault block up and down, It was more than that. There were mountain ranges there that, yeah, were dislodged by extensional tectonics, but the makeup of those mountains were similar then as they are today. And now this leads to thinking about, well, question at the bottom of the page, what was the landscape and compositional makeup prior to Eocene extension? Can we go back in time? And now I have to bring into play zircon age analysis. That's going to get us farther down that route. And I guess as far as background, I don't know if everybody's up on the tetrahedral zircon analysis or not, but fundamentally, you can obtain the crystallization ages of zircon by means of radioisotopic dating with a uranium-lead isotope systems. This tells you the crystallization age of the grains. So leading left to right, in the case of plutonic and volcanic rocks, it tells you when they were crystallized. And that has a real utility in basin analysis. If we look at the diagram down here, now, yes, this is a foreland basin, and I can't see my own pointer. Is the pointer still working? There. Wait a minute.
Can't see it.
Yeah, but the pointer option box came up. I'm going to change it. I want to change it to a laser if I can. Okay, there we go. Perfect. Is that more seeable?
That's good.
Yeah.
Yep.
Okay, so yeah, this is a foreland basin, no big deal. But what it shows is an uplift with a plutonic core, plutonic zircons crystallized within that, and that these can be transported overland into a basin as such. You can have contemporaneous volcanism, volcanic zircons, marking the time of deposition. And there's also the possibility or the reality of getting zircons from country rock, which I refer to as recycled zircons in the basin. But in looking at these, in this case here, you have plutonic zircons related to the crystallization age of zircons in the pluton at the time of erosion and deposition. Not necessarily now. Now we could go up into the Flint Creek Range, take a sample. You'd like to think that's the same zircon age makeup as back then. In fact, that's the assumption we started out on. But no, the best you can do is really say that age reflects the age of the rocks in the pluton at the time of deposition or erosion and deposition. That age is much older than the deposit itself. However, if volcanism is contemporaneous, as it was for much of the time during the Renova, these volcanic zircons are going to give us the age of the deposit. And in this case, we'd refer to this as a maximum depositional age that reflects the oldest these rocks can be. And in this case, they're as old as a contemporaneous volcanism. And I'm not going to really deal with recycled zircons today. They're not going to come into play with our further consideration. So we have direct aging for the plutonics, volcanic rocks, the sedimentary deposits. You can use them to determine or reflect upon the age of the deposit to get what's called maximum depositional age. In the case where it's contemporaneous, it's rather precise regarding depositional age of the sediment. Okay, don't let this blow your mind. As I've entitled at the top, detrital zircon evidence for pre-Eocene Deer Lodge Basin and pre-Eocene Pluton exhumation. So what I'm trying to get at with this slide is to think about or make an interpretation that an intermontane basin, an erosional surface, was present in the Deer Lodge Basin and by inference in the other basins prior to deposition, prior to extensional tectonics. And also the fact that during that time before deposition, all during the Paleocene erosional unconformity development and the early Eocene, there were plutons being exhumed. Okay, so let's take a look at two samples. These are key samples. We've got, this is a geologic map for the region. Not much to see other than here's a sample site. That's for an axial fluvial deposit on the western side of the basin. And we've got another sample over here from a debris flow, which descended from the Boulder Mountains. Okay, let's take a look at some of these properties first. In that debris flow, there's granitic clasts, and the zircons give a maximum depositional age of 53 to 51 MA. That is the age range within the age range of the lowland creek volcanics. So this debris flow was deposited at the time of lowland creek early on in the time interval of lowland creek deposition. In fact, 53 to 51 MA detachment on the Anaconda detachment is thought to be about 53 MA as a result of Foster's and others' work. So this deposit is very old. It's documenting transport off the batholith. And in addition to these volcanic related grains, here's the detrital zircon plot for that sample. We have a 76 MA peak, or a mode, if you will, that matches the Boulder batholith. So we know that 51 to 53 million years ago, the Boulder batholith was already exposed and supplying detritus to the basin. Similarly, if you come over here to this axial fluvial deposit, this one is particularly of special importance because this does unconformably set upon a granite thought to be the same as Boulder batholith granite. So it sits right upon the unconformity surface, right upon the erosional surface, and the maximum depositional age, because of volcanic grains for that, is 54 to 52 MA. The oldest grains are 54, which is equal to or a little bit older than the time of detachment in the Anaconda system. In addition to that, it contains a 76 MA mode or detrital zircon group, which is related to a plutonic source. And here I show the Boulder batholith again because of what's interpreted to be, this is interpreted to be Boulder batholith type rocks. Shows that it's dead on with that, but also up in Lost Creek, the Lost Creek pluton, which is just north up here a little bit, there is it looks like about a 77 MA group. It's essentially the same. The reason that peak doesn't stick down very far is because in that same pluton, there's an abundance of 40 MA grains. So it's a proportionality thing. There's two modes, one in the mid-70s, saying that these are plutonic derived grains, or pluton derived grains. And this here, and right away, you can see, well, why is none of that up here? Where's the reflection of that? That's a little bit into the future of this talk. Why these modes are missing in the Renova deposit, these younger modes. Anything else? Oh, here I'm resting on detrital zircon data to say that the boulder batholith and at least the Lost Creek pluton and this one here were exposed. Well, this is detrital zircon data. Don't forget the basin margin deposits up and down along the line also have granitic clast in them, and we know they came from the mountains. This is just more of a quantitative approach to say the same thing. Oh, point that I didn't mention. This axial fluvial deposit is sitting right on this granitic body in depositional contact with it. And the fact that that granitic pluton is exposed, if one considers thermal barometric data for the region, this implies that greater than 10 kilometers of crust had to be removed before deposition of fluvial sediments occurred on top of this, which would require a significant amount of geologic time. So what is that saying? Oh, it's likely that these axial systems incised down through time into the infrastructure, removing crust, and that the floor of the basin is not just instantaneously produced by extensional faulting, Horst and Graben style faulting. Okay. Is there any other evidence of this? And I put this in here. I went back and forth. Do I put it in here or not? Because it's not convinced. Is this little where this meeting is being recorded? Is that in front of you all? Do you see that at the top? Is it blanking out? It is?
Yeah, it says suggestive evidence.
Okay.
Yeah.
So is there any other reason, any supporting evidence that these basins might be fluvially incised? And this is not great data. It's based upon gravity and seismic studies. And you just sort of have to take it for what it's worth. But if you look at the overall shapes of these transects, take these on the left. This is from gravity data by Partner and others. This is from Rowe's thesis, his cross sections. And in each case, it was suggested that they're fault-related basins. Yeah, they're fault-related, no doubt about it. But are they fault-generated? And I put a black line underneath these little Fs, not thinking that probably you couldn't see them, but in this profile here, the author suggested, well, that's probably a fault running down like this. And Rose on this side said, oh, in the Northern Big Hole Basin, that's probably a fault surface air running down. And this could be interpreted as a fault, and this could be interpreted as a fault. You can't really see the fault in the outcrop or on the Earth's surface. But if you look at the overall shape of the basins beyond that, they're reasonably shaped. And then here's the North Boulder Basin. They're reasonably shaped to be intermontane valleys, fluvial incised intermontane basins. They can't prove anything in themselves, but once you couple that with the quantitative data from the Deer Lodge Basin, things become a little more believable. Okay, so, and Colleen, can you tell me what it says underneath the gray thing? Probably not.
I'm not sure what you mean.
Oh, the title. I can't even see.
Oh, it says
my slide.
granitic plutons and detrital zircon sample sites.
Okay, yeah. So now I want to shift to a consideration of the granitic plutons flanking the basins, and to consider them in terms of their crystallization ages for the plutons themselves and their detrital zircon signature within the Renova deposits. So shown in red are all the sites at which we collected detrital zircon samples or compiled them from the literature, pre-existing data. And so let's see, anything else to point out here? I've broken the area down on what I refer to as an eastern region, like this, which really includes a boulder batholith here, boulder batholith here, and the eastern or the East Pioneer Mountains batholith here, and the western region encircled in red that includes the Plutons and the Flint Creek Range and those within the Anaconda Range. And we're going to see marked differences between the signatures, between the plutonic zircon signatures, that is, the zircons from the plutons themselves between the two areas. And then we're going to see significant differences between the igneous rocks here and their detrital zircon products here. And again, this is a region that I've referred to. ARP, we're no longer using that. We use ADZ for the Anaconda Detachment Zone. Okay, so the eastern region versus the western region. Let's just look at the age makeup, the zircon age makeup of the plutons themselves in the eastern versus the western region. So here's the eastern region. There's a plot for the Boulder Mountains, the Boulder batholith, and the East Pioneers batholith. And you can see that they look virtually identical. They're unimodal, fairly tight zircon age distribution. The age in the Boulder Mountains or Boulder batholith, 76 MA, and in the East Pioneers, 71. So a little bit different, but both late Cretaceous, unimodal zircon age distributions compared to the western region. If you look in the Flint Creek Range, here's the zircon age distribution, and I've just identified peaks. We refer to these as zircon age groups. We consider the groups with a peak. We don't think just in terms of the peak age itself, but it makes it easy to refer to. Here we have a 75 MA group, a 68 MA group, and a 40 MA group. Okay, if you go down to the Anaconda Range, here you have your 75 MA group again. Now, these are composites of plutons. 75 MA group, 61 MA group, and then a little bit of chattering down here. Now I'm going to change plots on you. These were frequency plots, the bars, and the red lines are the probability plots associated with the frequency distributions. Let's go down here, and these are just probability plots. You can just imagine the frequency distributions lying underneath them. Now, I'm going to talk about detrital zircon age data. Zircons in the deposits indicated by the black lines versus the age distributions in their source rocks, in their plutonic source rocks. Now, the first obvious question is, whoa, how do you know the detritus comes from a particular plutonic source area? So that's why I put this in here as a reminder. When you combine facies with paleocerns and cobbles in the basin margin deposits, they tell you where the source area was located. And therefore, you know what plutons existed in that particular source area. Now, if you can group your detrital zircon data so that you established deposits which are linked with those particular source rocks, we can compare the zircon ages in both. And I hope I was clear on that. It's possible to link these deposits so we know they also came from these sources. Not in all cases are the detrital zircons from a basin margin deposit. They might be from axial, but in those axial deposits, we may have two mica cobbles that had to come from the Mount Paul batholith, for example. So let's take a look at this. Here's our eastern region plutons and the detrital zircons in the basins. Here's our first plot for the Boulder batholith. The red line in all cases is Pluton data, intrusive data. There's the distribution for the igneous ages. The black line is a detrital zircon signature for the deposits that came from that pluton. Perfect. Works like a champ. Both are unimodal and fairly well constrained, narrow distribution. Let's go down to the Melrose Basin. Well, the detrital zircon plot for the deposits linked to the East Pioneers is a lot messier, but easy to explain. These are all recycled zircon grains that are associated with late Cretaceous deposits, such as, come on, Bob, you can, Blackleaf Formation deposits and Frontier Formation. These are ages associated with Dillon volcanics. This here is the range of the plutonic pluton source zircons. The red line is the East Pioneers batholith, and the black line are the ages in the detrital zircon deposits that are associated with this. So again, good agreement. The more samples you would have of this, I'm sure this would fill up and look just like it. But we're stuck with what you got. So the point is, well, I have the summary slide in a second, and I'll get there. Let's go to the Western basins. Oh, heck breaks loose. Flint Creek Range. Here's the multimodal igneous age distribution here. And here's the detrital zircon plot associated with it. That detrital zircon plot is reminiscent of the eastern basins, similar in age, similar in shape, but its potential source rocks, at least in our mind initially, was, hey, these are the source rocks that we know are linked with these deposits, but they have all these younger modes. Why are they not in the detritus? Why are they not reflected in the detritus? Go down to the Anaconda Range and the Deep Creek Basin alongside of it. Same thing, multimodal. And here's your Cretaceous mode right there in the igneous rocks, matched by your detrital zircon mode. So here's this consistent pattern. You can group and regroup your samples in a number of different ways. I've just put in summary slides, sort of batching things together to show you what the results look like. Okay, so let's combine things even more in this upper plot. Now I've combined the North or the Flint Creek Range plutons with the Anaconda plutons. And the red line is the composite detrital zircon age distribution for all plutons where we have data in the Flint Creek Range and the Anaconda Range. And you can see these multi or polymodal spikes, a hint of one at 93, one at 85, 75, 67, 61, and so on down the line. If we compare it with the detritus, which again is just a summation of the previous two slides that you saw, you have this well-established 76, 77 MA detrital zircon mode. It's a late Cretaceous mode. And then all these other peaks are virtually absent other than this 50 MA here. But again, that's Lowland Creek volcanics related. And that can be established by looking at the deposit and say, oh yeah, there's volcanic detritus in there. And it matches the Lowland volcanic age signature perfectly. So here's this mismatch again. Bottom line, hey, there's a late Cretaceous mode, and that matches, but all these modes are missing. And thinking about this, you could say, well, hey, wait a minute. Here, there's a bunch of plutons in there. Some of them are 2 mica plutons, and one, there's other non-2 mica plutons, so biotite, hornblende, granites, and so on. So in trying to be more specific, what if we look at just the 2 mica detritus that we know are coming from two microplutons that you can go and put your hand on today. How do they compare in the age distributions? Well, the red line are the igneous ages in the two microplutons. And once again, here's the two mica detrital sand. Okay, it's two mica detritus, and the only match you get is in the late Cretaceous mode. So there's something to this. During Renova time, unless they're not the same plutons, which I don't know how they can't be, okay? During Renova time, you're just getting late Cretaceous detritus, and you're not getting any of the younger detritus. Let's look at this through time, and we can't do a very good job, but we can do a job, get some idea. Down here at the bottom, we have the Deep Creek Basin data. We just looked at that in the previous slide. Here's the multimodal Anaconda range plutonic data, the single mode in the detritus. And it turns out there's only a couple samples available. There's a sample from the 6 Mile Creek Formation from, I said Howlett. Is that, I don't know if that's right. For some reason, I think, no, it's Rowe's detrital data. I saw that and got confused. It's a sample that Rowe took in his master's thesis. And up here, we have a sample of modern sediment on top of the batholith, of the Pintler batholith in the Anaconda range, a sample that Link took. And let's compare the distributions through time. So we're starting out in the Oligocene here. Deep Creek Basin. The width of this bar shows the span of detrital zircon ages in black from this longer red plot. Here's a span of detrital zircon ages, which are present in the Oligocene. When we come up to 6 Mile time, the black band is much wider, and it matches this red line plot. Howlett's data comes from the Pintler batholith itself. So this is really a good match. Pintler batholith rocks and Deep Creek Basin rocks, all two micas. But we can see that the age range of detrital zircons is increasing during 6 Mile time. And then we have this deposit from the modern, the stream draining the Pintler batholith shows a much wider occurrence, 50 MA to 80 MA igneous derived zircons compared to, and this would be the igneous age plot for the Pintler batholith itself. Okay, so we're getting younger and younger detrital zircon groups as we go through time. So initially we had this dilemma. Down here in the Renova, just a single late Cretaceous age group. Now as we go through time, we're getting younger and younger age groups. And let's see, what else did I want to point out on this? I guess that's it. I lost my thought. Summarizing this a different way, and I know there's too much deal here to appreciate it. How do I get rid of you guys? Can you see the far right side of the slide? I guess you don't have to. I'm all covered up.
Yeah, we can.
Okay, good. So this is a time chart, and on it I've shown the chronology of magmatism, pluton exposure, and deposition. Okay, time on the vertical axis. Here's the approximate time range on Renova deposition, 54 or 53 to about 17 MA. 6 Mile Creek here. And in this column here, again, blocked out, that says magmatism.
It's plutonism.
Or plutonism. Okay, same thing. Magmatism, plutonism. These are the age ranges, or the ranges and ages of all those little spikes that I showed in the igneous data. There were a few grains down here at 93 MA, more so around 85 MA. There's a little clustering of grains here. Oh, great abundance. With a 75 peak, the range is about 70 to 80 MA and a 68. So it must be there are multiple magmatic events through time. These are crystallization ages that took place prior to Renova deposition. And then during Renova deposition, here we have the 50 MA group and the 40 MA group. So while the Renova is being deposited, we had magnetism going on at the same time. If you look at these ages here and look at the tridal zircon ages, what we see is that in the Renova, over here, these age groups are these age groups. So during Renova time, we're only getting older crystallization ages from earlier heating events, thermal events, magmatic events. Those rocks are made it to the surface and are being eroded and depositing into the Renova basins. When you look at detritus after the early Miocene unconformity up here, we're getting all age groups being deposited in the 6 Mile Creek basins, so to speak. So younger ages are being added. So the question is, how does this happen? Okay, summary, and I'll just zip through this because I don't think we really need it. Summary so far: plutons, eastern region, single plutonic age, western age, multiple ages, up to 7 groups, 5 to 7 groups. When you compare it with Renova deposits, in the eastern basin, single plutonic age, single tridal zircon age at Magus, late Cretaceous, and both. Go to the western basin, here comes a discrepancy, multiple age plutons, but just late Cretaceous detrital zircon ages. If you're more specific and restrict yourself to 2 mica plutons, same deal. Multiple pluton age groups, just late Cretaceous ages. Time trend, as you go through time, you get younger and younger ages being delivered to the basin. You retain all the old ones, but you add new ones. So how does one account for this? So I put together this exhumation model. And your brains are probably fuzzy by now, mine is. In this model, let's see, pink indicates pluton, granitic pluton. Left to right is time. We're going through time, stage 1, 2, 3, late Cretaceous, Paleocene, Eocene, Middle Miocene, and so on. This arrow indicates the pluton is tectonically rising through time, such that when you start out in the late Cretaceous, the plutons are buried, let's say up beyond 10 km depth, 10 kilometers depth. But then through time, they're going to become exposed and progressively more and more and more exposed through time due to uplift and downward cutting, simple erosion in the mountain belts. Now, all this junk here, what is it? Well, late Cretaceous, here we have our 75 MA group being developed, crystallized. It's in the subsurface. But as time goes on, the igneous groups, the plutons are being uplifted, and those with a late Cretaceous signature are being made available to the surface and being eroded. But wait a minute, this is a Paleocene. We don't have any Paleocene sedimentary rocks. What would happen to them? Well, my answer is they were flushed out of the system by fluvial systems, transported right out of the system. Go to the Eocene. Now Renova deposition begins, and we're cut farther down into the Pluton, but we're still in the upper regions where only late Cretaceous igneous zircons are being made available and being transported into the adjacent basin down here in the Renova Formation to getting a 75 MA group, plus older groups that were already there. I'm leaving those out of the story. Here's a 6 Mile Creek Formation, 6 mile time. By the time you get over there, the plutonic complex had uplifted even more so that you don't just have Cretaceous, but you're getting Cretaceous plus Paleocene, and then Cretaceous, Paleocene, Eocene zircons being transported and deposited into the basin with these age signatures. And then eventually all of them exposed through time. Now, we don't have enough data. This is something for the future, for somebody to do in the future, to sample the stratigraphic section in greater detail and see if there's a nice, straightforward progression like this. All we know is we have this, a sample here, a sample in here, and a sample up here to define this trend. Okay, I want to leave this slide. Are we okay with that?
Yeah.
The answer is yes.
Okay, so drawing all this to a close. Summary slide at the end of the talk. In this diagram, it shows time from the bottom towards the top. And down here, this is pre-Renova deposition. Late Cretaceous, maybe, but certainly all during the Paleocene into the early Eocene. What I'm proposing is that there was fluvial incision. Remember, this is in the fold thrust belt, severe fold thrust belt. And during that time period, there was fluvial incision into the active thrust belt and the moribund, and then eventually the dead fold thrust belt. And it didn't last too long in that stage, but it resulted in intermontane landscape and longitudinal drainage network development. At this time, the ancestral headwaters of the Missouri River developed. Now, we don't have no sedimentary deposit evidence for this, but all the other evidence, hydrotidal zircon evidence I went through, in my mind, pretty well establishes this. The basins were flushed, I'm proposing, because of the topographic gradient, and it was a PETEM, the Paleocene, Eocene thermal maximum, a warm, wet climate, abundant water to flush the systems clean and produce the unconformity that upon which the Renova lies. A valley-shaped unconformity that runs up onto the flank of the mountain belts. We could have talked about that a little bit. And during that time period, Cretaceous plutons were exhumed much prior to detachment in the Anaconda detachment zone. Now, these two images, this is common. This process here is the standard, well, forget the plutons, but 1, 2, and 3, that's standard fare in all modern active fold and thrust belts. It's just the process response that goes on in the systems. To the left here, this is a shaded relief map of the Andean fold thrust belt in Bolivia. And it shows drainage patterns akin to the paleo drainage pattern that I showed earlier in the talk. And what I did was measure topographic profiles across here, the Zagros fold and thrust belt, a number of thrust belts. This profile here is from the Bolivian fold and thrust belt, and it shows a profile similar to the Montana topographic profile, but these are incised basins in an active fold and thrust belt, and the name for those basins, the term given them, are piggyback basins. They develop on top top of active orogenic wedges. They may be empty because they're flush clean, to partially filled to nearly fully filled. Okay, let's go into Renova time. Okay, starting with the Renova deposition, at the same time, cause and effect, there was extensional reactivation and breakup of the foreland structural framework. The Anaconda detachment transected granitic plutons that were exposed in the adjacent mountain ranges. I had to necessarily, as well as associated high-grade metamorphic rocks that were associated with the plutons. You can see that in outcrop today. So that attachment surface cut through these very plutons that were already exposed. At the same time, basin subsidence and filling began, Renova deposition. And let me see. The detritus was only late Cretaceous granitic detritus, but at the same time, plutonism was going on at depth beneath the same igneous complexes. And what I did here is I took the profile from below, use this red line as a reference line. Down below, it connects the Tallweg or the bases of the intermontane basins or the piggyback basins. And I said, okay, let's take that profile and subside it and stretch it a little bit. The structural geologists would go nuts with my work, how bad it is. But let's stretch it and subside it and fill it up. And these would be the Renova deposits that you see today. And this would be the basin and range, which conventional thought is that, oh, wait, the basin and range is created by extensional tectonics. So basically what I'm saying, wait a minute, it's a two-stage process, initial development as such, and then extensional reactivation of contractional structures as well as initial break or new breakup of the foreland to produce what is this basin and range topography and intermontane basins we have today. That's it. That ties everything together. I don't hear any snoring.
Yeah.
Pardon?
So, are you willing to take questions?
Oh, of course.
Okay. Let's start with the people in the room here, or should we start in Zoom land? Anybody in Zoom land got their hand waving? No. Okay. Anybody?
I'll ask Bob. So denudation rates, is there any place that you would be comfortable calculating some denudation rates just to back of the envelope, get a feeling for this exhumation of rocks?
Did you hear that, Bob?
Yeah, I did. And I took a stab at it in this manuscript, which is undergoing review right now. Again, Teresa and Colleen and myself. But I'm fuzzy-headed enough. There's an implication of rates. And related to that, what I can remember best is that by the time Renova deposition started, there had to be 10 kilometers of exhumation by that point in time. So figure out, how you would do that calculation. I don't know. You have late Cretaceous plutons, 75 MA, that are being exposed. And in order to expose them, you had to remove 10 km of overlying crustal material. I don't know how you'd calculate that. But, I mean, there are some numbers. And you can do, Foster and others gave numbers for continued uplift in the Anaconda Flint Creek range. And I can't remember what I had to say about that. I just can't remember. Maybe Colleen could dig those numbers out at work and share them with you.
Just
over a
curious.
beer.
Yeah.
Jan?
Well, I was just gonna say that any piggyback basins, whether it's flushed out, there's always a basin preserved somehow. I don't think you can find like an analog in the Himalayas or Bolivia where there's not a piggyback basin being
I
preserved.
can't quite hear this.
Okay, he said that there's no piggyback basin in the world that doesn't have a basin there, sediments. Is that what you mean?
Yeah,
Like that is not collecting
it's not-
sediments?
It's not always.
It's not always flushed.
Yeah, there's
he
always-
says.
No, it's not. That's what I said. They can be, they can range from empty to nearly full.
But are there Paleogene sediments?
Well, we don't know. He's asking, are there Paleocene sediments?
Oh,
And
yeah, we're stuck with what we can see and
it was, yeah. I would argue that there are exposures of there are sediments underlying the Lowland Creek that have not been very well studied. And so there could be. There could be.
but so I guess what you're asking is, could they really be flushed? Is that unrealistic? Is that what you're asking, or is that what you're wondering?
Yeah, I think, well, there's ways, to flush a system, you need to have a huge amount of incision rates.
He says,
It's like a Tibetan plateau sort of stuff, you just have a huge amount.
yeah, he says that to flush a system like that, you need a really high incision rate.
Oh, yeah,
Like-
I agree. Yeah, and see, the way I thought about it is you have this unconformity surface, which is really where it's an unconformity, not where it's a structural contact. But let's say it's a fluvially incised surface, as you see in active fold thrust belts today. Okay, and it sits upon, in Montana, in southwestern Montana, it sits upon deformed, contractionally deformed Mesoproterozoic through Mesozoic rocks. So, and we know that some of those rocks, the plutons in particular, were buried at, let's say, greater than 10 km. There had to be a lot of incision. And when did this occur? Oh, it occurred in between the late Cretaceous and the early Eocene during the PETM, when things are, I mean, not only was it a mountainous area, but there was an abundance of water, and there the ingredients are really active incision and flushing. And why does there have to be flushing? Well, because where are the sediments? Now, there may be some, but that's even better, because if you look at articles on modern fold or active fold thrust belts, the basins range from empty to partially filled to filled. And some of the ones, at least they report that were partially filled, had been flushed out by high runoff events.
Well, the only thing is the peak exhumation rates are older than 75. So,
No,
no, I mean, there's not a whole lot of the high incision rates tied with exhumation rates. That's in the Paleocene.
According to what?
yeah. So he's saying that can you come here and talk to?
The peak exhumation rates are not in Cenozoic.
He says the peak exhumation rates are not in the Cenozoic, but he just said they are, so.
But, well, why are they not? They're not all during the Cenozoic. Cenozoic's a long time period, or
Yeah,
I'm saying it was high during the Paleocene through early Eocene.
you got him stumped there. Okay, Stuart, question now.
So in east central Idaho, I know Dave Rogers and Janicki made a paleogeologic map beneath the Eocene unconformity. Has anybody done a similar geologic map beneath the Eocene in Montana? That you know of or started doing such thing?
Could you hear that, Bob?
Yeah, I don't know of any. I saw their map. I looked at it. Well, looking at the southern basins there, but no, I don't know of anything available.
That'd be interesting.
Now-
Yeah,
Go
that'd be
ahead.
interesting to make that and splice them together and then sort of try to quantify, how widespread and how much exhumation. Because I know there's a lot of evidence in East Central Idaho that pretty much across the board, like everything's been exhumed like more than 6 kilometers. And they have the same problem where there are no, Cretaceous even sediments in the piggyback basins in East Central Idaho. They've all been completely eroded and flushed out apparently. So anyway, something else to do in the future for you.
Yeah, not my future.
So is there anybody in Zoom land who would like to ask a question, make a comment? Just unmute yourself and speak up. Nope,
I have another quick one. That's okay.
Stuart.
So I know that there are some fine grained debris flows in the Renova, correct?
Right.
Okay, so you didn't mention those. So where do you typically find those, and are they, how do they relate to different sources, and how do they relate to sort of different positions in the basin?
Actually, I don't have any good examples in these western basins, but if you go over to the North Boulder Basin, actually the North Boulder Basin, Jefferson Basin, let me think of the name of all the basins over there. Three Forks Basin, there's premier examples of mud flows. And are you familiar with Red Hill?
Yeah, yep.
There's some good examples there, and there's directly analogous red mud flow deposits in the basins that I just named.
Okay.
And they lap right on what would be ancestral uplands along the basin margins. And they're intermixed with the coarse-grained debris flows too.
So in the basins you're talking about in this presentation, there pretty much aren't any fine grain?
Well, I can't say that.
Not many?
They may be there. I didn't see them.
Okay.
Well, I can't say that. And up on Spring Creek, oh, what's the name of the outcrop area? Colleen,
You mean on the,
on the Flint Creek side,
on the front, yeah, what's the Modesty Creek, off the Modesty Creek Road? Is that what you mean?
yeah. There's a vertical succession there that there are mudstone units with some paleosols in them, which I suspect they're probably mud flow deposits. There we concentrated on carbonate clast debris flows and fluvial tributary deposits with siliciclastic clast within them. We didn't find any granitic clast there, even though we had igneous plutonic zircons in those deposits. But that's the only place. It doesn't mean they're not there. I just didn't see them, and it seems if somebody wanted to go out, if they wanted to, they could search them out and find them.
All right. Anybody else? There's a lot of exploded heads in this room. So your job well done, Bob. Thank you
Thank you
Okay.
very much.
Okay, thank you very much. So I guess we're checking out.
For checking out. Yeah, I'm
Okay.
gonna stop.